Hi everybody, we're going to go through some notes on solids, liquids, and gases and phase changes. Basically, a phase change is just a substance going through the different states of matter, from a solid to a liquid to a gas, or a gas to a liquid to a solid, or you can go from a gas directly to a solid, or from a solid directly to a gas, and those are part of the phase change diagram that we'll be getting to coming up here shortly. But a quick review, we've done this before. Physical change is you don't change what the substance is. If I take a log and I chop it into two pieces, it's still the same thing. It's the same chemical composition. If I take that log and burn it, that's a chemical change. It releases smoke and heat, and you're left with ashes of carbon. So it's a different product. You don't have the same thing as when you started. So physical changes, you just change the shape, you change states, you see to go through phase changes. A chemical change, you actually get new products at the end. If you hear a little wind in the background, I am at the cabin and it is really, really windy tonight, so that's what you're hearing if you are hearing stuff rattle. So if you take a look at this picture, this is a geothermal spring and they are running a power plant off of it, and people go because they think it has some healing powers, and warm water often does, so I wouldn't dispute that. But you can see steam, gas, you can see liquid water, and the people are solid, and the plant is solid, and the rock behind it are solid. So you can see three phases of matter. If this helps you, I do have a link in here to the BrainPop states of matter. I'm not going to take the time to show that, but it's there if you want it. So a solid is an orderly repeating pattern where as you've removed enough energy, they start to form these. In this case, water forms a crystalline shape, which we'll get to in a little bit. It's the big oxygen with two little Mickey Mouse ears, which are the hydrogen, and then the oxygen and the hydrogen, and anyway, it does a nice repeating pattern. Water is interesting because it's basically the one substance that, there are exceptions, but it's the one substance that when it gets cold, it expands. That's why we don't put a bottle of or a can of pop in the freezer for very long, or you have a big mess. Or in Minnesota, you don't leave it out in your car in the middle of winter when it's below freezing because, well, the water freezes and explodes the can or the pop bottle. So what you have in a solid is you have molecules that are vibrating, but they're not freely moving around. And if I add energy to it, now the molecules can start to freely move around, and we have a liquid. They're not in that crystalline shape. So in a liquid, we have movement, and the more energy we add, the more heat we add, we can get those molecules to start to move so far apart they can escape the surface tension of the liquid and form a gas. So what do you see in this picture? How many different states of matter? Well, obviously we had water vapor going up to condense into those clouds. So we've got liquid water. Actually, technically, it's liquid water in a cloud, but you had a gas to get it up to that point. You have liquid in the lake. This is, by the way, my cabin. This is a number of years ago because I haven't had the dock out in a couple of years. We have solid. The dock is solid. The boat is solid. The ground is solid. The tree branches, the leaves are solid. But the lake is liquid, and we had a gas to get those clouds to form. And technically there is a fourth state of matter, and that's plasma, and that's what the sun generates. And we like that because it keeps us warm. Not tonight. It is not warm up here tonight. This is the same lake. It's the same dock. Here's the little bench, but this was one of those where you do the panorama, and so it kind of warps the image into a curve, and it actually should curve the other way. But you can see here again, you can see clouds, you can see the vapor, you can see the water, and you can see solid dock and land. This one I want to show you because I actually recorded this morning. And you can see solid land in the background, but you can also see solid swans. And we can see liquid water. The one state of matter we're missing here is what? What don't we have in here? If you said water vapor, you got it. So we have liquids and we have solids, but we don't have anything else. I was like 30 feet away from them, and they just kind of swam towards me and kind of stopped in front of me and let me videotape them, and they just went around eating some stuff off the bottom of the lake. And there was another one coming in. I think that was one of the parents, because eventually it caught up to them. It was like they were on lookout, and they did the neck bobbing. It was kind of cool to see. Anyway, states of matter and swans. Gotta love it. Something like this probably going to be on your test, where I'm going to have some kind of picture for you to identify. We have steam coming out of a geyser, that's our gas. We have liquids in the pools that are collected in the rocks, and the rocks, of course, are our solids. Let's see if we can get this run. I'm not going to play the whole thing, but this is a quick review of what we just talked about.
The states of matter are gas, liquid, and solid. Gases assume the shape and volume of their container. Particles of a gas are separated from each other, move in straight lines, and in a completely random manner. They change direction only when they collide with each other or the container. Liquids have a definite volume and assume the shape of their containers. The particles of a liquid are closely spaced, and so their motion is still random, but much more limited. The particles slip past and collide with near neighbors. Solids have a definite shape and volume. Particles of solids are in fixed positions and collide only with near neighbors.
Okay, so what they were just talking about is really good on a test. Solids have a definite volume and shape. You need to know that for the test. That's the difference between a solid and a liquid. Solids have definite volumes and definite shapes, and they do vibrate, but they only really collide with the neighbor next to them. So a pen's volume could be 6 cubic centimeters. Its shape is cylindrical. No matter how or where it's placed, it still has that same volume. Water, if it's liquid form, takes the shape of its container, but solid water goes into its crystalline shape. So solids have a definite volume and a definite pattern. Particulates in a solid, they're packed closely together. They're fixed in one position. They have, again, definite shape, definite volume. I've said this 20 times now almost, so it's obviously important for the test. And they vibrate, the particles vibrate slightly back and forth motion. There are different types of patterns. I said they form an orderly repeating pattern. Well, that's true in a crystalline solid. They do form orderly repeating patterns. We can tell different crystal structures, and we can tell, what crystal is what just by sometimes its shape. It's one of the good points. But it melts at a distinctive melting point. So that's another thing about a crystalline solid. And a crystalline solid versus an amorphic solid. Amorphic would be like wax or silly putty or plastic. Crystalline shapes have definite patterns. Amorphic solids have no specific pattern. And then there's polycrystalline, but we're not going to get into it. Really, we're going to talk about crystalline and amorphous. So amorphic solid, a solid particle is not arranged in a regular pattern. There's no good way to draw it except that it's not regular. Wax is, again, one of those examples. And they don't have a distinctive melting point, but they do get soft when it gets warmer like plastic does. And it's able to be molded into many shapes. So there's a lot of benefits to an amorphic solid. Now, liquids. They have a consistency of that of like water, oil. They flow freely, but at a constant volume. But they don't have a definite shape, but they do have a definite volume. And you'll notice that their particles move around, but they're still bumping into each other. They don't have a lot of space because it's still a liquid, but they're packed almost as closely as a solid, but again, they move around much more freely. No definite shape, takes the shape of whatever container. Without a container, it flows into a big puddle. It doesn't easily compress or expand, but it does, again, have a definite volume. I can measure that volume. Now, let's go to viscosity. So that is the state of being thick or sticky or semi-fluid in consistency due to internal friction. Particles are free to move around, and how resistance to flowing is kind of the definition of viscosity. So water has less viscosity than honey. If you look at this, these are the different types of lava in Hawaii. This is a much more viscous lava than this one that's oozing and creeping. This has more internal friction causing it to move slower. And there's a fly in here because we have the door open because I was getting my front door replaced today. So yes, the flies found the inside. If you you've never seen this, these are some old videos that I still really enjoy. But if you take a look, this actress, some of you may know, she plays Dr. Bailey on Grey's Anatomy. if we can get it to work.
You know, the
Sometimes
problem
he's
with
paused. I might have to start it
chemistry
again.
is that it's so darn obvious. And you know what this is, right? Viscosity. Great for motor oil, but lousy when you're in a hurry and want to eat breakfast. Now, we're talking viscosity here. Oh. Well, how can we avoid this process? Here, let's go to the track and find out. Now here we have 3 well-known liquids: pancake syrup, motor oil, and colored water. Now which is which, and which one will run the furthest in 5 seconds down the track? Wow, but can we improve on this performance? You bet. Our 3 liquid friends have been lounging in this pool of water for a while. Let's see if their performances will change.
And it's warm water. You can definitely see a difference. So if you warm it up, the viscosity can change. Oil viscosity. If you are in Alaska in the middle of winter, you want a different type of oil than if you are in hot Arizona desert. You want a different viscosity. Gases, like an air. So a fluid substance which can easily, freely fill the space available, irrespective of its quantity. So in other words, if you give it more space to expand into, it just thins out, kind of like the upper atmosphere. It's much thinner than down here at the surface, where more of it's getting packed together and it's closer together. So gases move around freely in the space available. So if we were in a classroom filled with, a certain amount of space, the air takes the shape of that container, which is our classroom. And if we had it totally sealed and we released more compressed air, we'd have a greater density. So it would be possible. I mean, we don't have an airtight room, so that's not going to happen. But gases can change volume easily. We can compress them and put them into scuba tanks and take them underwater to breathe. In fact, the interesting thing is when you compress air, the molecules rub together and they generate so much heat that they actually have to put those tanks in a water bath of cold water to keep the tanks from exploding. So they can spread out or squeeze together to fit the container. Volume and shape is that of the container. Individual particles fly off in all directions at high speed until they run into something else which deflects it back. They fill the space available. It has neither a definite shape nor a definite volume. So that's a big deal. Solids have a definite shape and a definite volume. Liquids have a definite volume, but an indefinite shape. And gases have an indefinite volume and an indefinite shape. So that's the difference, and they also move around. You'll notice even just by looking at this, those molecules are farther apart and they are moving much more rapidly. So let's get into the phase change. And the interesting thing about this, and I like this a lot more than the old phase change diagram, because it shows that phase changes can go in both directions. So if I go from a gas and condense it, I get a liquid. If I go from a liquid to a gas, I have to go through evaporation. If I go from ice to liquid, it's melting. If I go from liquid to solid, it's solidification or freezing. And this is the one everyone has the most trouble with, so this is the one to pay particular attention to. If I go directly from a solid to a gas, that is called sublimation. But if I go directly from a gas to a solid, that is deposition. And that's where if we get to like 22 below zero and you take boiling water outside, we're going to show this, and you go outside, it immediately turns into a solid, but we'll talk about why that happens in a minute. Again, I've got another brain pop link here if that helps you on changes of state. So let's go through a really brief definition. Remember, all of this stuff, if you write down notes on the test, you can certainly use it, and it would be a lot easier because the next test, all your information will not be available to you, so make sure you're taking good notes. Melting, to make or become liquefied by heat. By the way, heat always flows from hot to cold, so that basically means all of that ice cream is absorbing the heat around it and melting it. So, change of state from a solid to a liquid depends on how strong its particles are attracted to each other. Adding energy changes the arrangement of the water molecules that form ice crystals to form liquid water. In this case, it's ice cream. But again, change of state from a solid to a liquid is your melting. Freezing. Temperature approaching at or below the freezing point. So changes in state from, you can see that going, that's forming ice. Change of state from a liquid to a solid. Water loses energy to the air, and the water molecules move more slowly because they're not vibrating as fast. And when the temperature reaches 0 Celsius, the molecules form a regular repeating pattern called ice crystals. Now, or in this case, water crystals. So freezing is the change from a liquid to a solid. And it does lose its energy to the air because it's warmer than everything around it. So it's giving off its heat, and that's getting absorbed by other things. So that's why if you put really hot food in your refrigerator, you can actually warm your refrigerator up and cause some issues with, spoiling your other food. Vaporization. So this is a little different. This is change of state from a liquid to a gas. Vaporization is what happens when water gains enough energy to break the surface tension and becomes a gas. Otherwise, I would technically call that evaporation. Vaporization is when it happens pretty quickly. Deposition. This is the one I was talking about. This was a very cold day in Minnesota, and I have to give credit to Mark Seeley. He's a climatologist at the University of Minnesota, and he explained the phenomenon. So here we're going to go through it because he explains it really well, so bear with me. I'm going to read this. Here we go. You can just watch him in the background. When it's cold outside, there's hardly any water vapor present in the air, whereas boiling water emits vapor very readily. That's why it's steaming. So when you throw the water up in the air, it breaks into much smaller droplets, and there's even more surface area for the water vapor to come off of. So it basically expands and releases its energy out. Now, cold air is very dense, and this makes it cool. It makes its capacity to hold water vapor molecules very low, and there's a justification then for the less space the vapor molecules. So with that fundamentally less space, it doesn't have anywhere to go, so it wants to condense. So when you throw the boiling water up, there's suddenly the minus 22 degree air. There is more water vapor than there's room for it. So the vapor precipitates out by clinging to microscopic particles in the air, such as sodium and calcium, and they form crystals. In other words, you're instantly forming snowflakes. Sorry about my reading blunder. It's apparently late and I should have gone to bed. But here we go. Thermal energy. Temperature is the measure of the average kinetic energy of individual particles of matter. Thermal energy then is the total energy in all the particles. So thermal energy. Temperature is the measure of the average kinetic. So when we take our temperature to find out if we have a fever, it means when it's higher, we have more kinetic energy. Your body is actually, burning more fuel to try and, boil out your virus or whatever it's trying to combat at the time. Thermal energy then is the total energy of all its particles. Again, good test question. Heat is the movement of thermal energy from a substance of a higher temperature to that of a lower temperature. And there's 3 ways to do heat transfer: conduction, convection, and radiation. We're going to be spending a lot of time over that over the next day or so. Well, actually the next couple days. So conduction, really quick review. Heat is transferred from one particle to another without the movement of matter itself, but you must be touching. So if you touch something that's warm, you are, through conduction, gaining that heat. Convection, on the other hand, heat is transferred by the movement of currents within a fluid. But a fluid a fluid is a liquid or a gas. Both are fluids. We actually walk through fluids all the time. It's just that that's our atmosphere, or atmospheric gases. So what happens is if there's a place that's really hot, hot air rises. And as it rises, it cools. Remember, this is from 8th grade adiabatic temperature cooling. If you were here with Mr. Cater or myself, anyway. And as air rises, it cools. and becomes more dense, and then it starts to sink where it comes close to the heat source, where it starts to gain energy again. Then it starts to rise, and we get convection currents within a liquid. And you can get convection currents like if you have a wood burning stove, the air above the stove is warm and you get convection currents coming. You also can have radiant heat from that too. And we have convection currents on our planet called Hadley cells. Remember, at the equator we have hot air rising, and we get those nice, southeast and northeast trade winds, and then we've got the prevailing westerlies and the polar easterlies, just to bring you back to 8th grade, just in case you've forgotten. But we have convection currents within our atmosphere. We have rising and sinking air. The sinking air occurs at the desert line, 23.5, go up, and you'll get that, and it also happens down south as well. Radiation then is the transfer of energy by electromagnetic waves. Do you like the fact that I stopped myself from going into a whole earth science spiel? So, radiation, electromagnetic waves, you feel the heat from the sun, but remember, there's no medium for those energy waves to convey their heat through space. It's just space. But electromagnetic waves can travel through space, and they hit your skin or your shirt, and you absorb. So if you're wearing a darker color shirt on a sunny day versus a light color shirt, light color shirts are going to reflect more light back, where the darker shirts will absorb the energy and make you feel warmer. So you feel heat from the sun or a bonfire through radiation. So radiation is that radiant of heat moving through. At this point, normally I would stop and have you watch the Eureka conduction convection radiation video, but you're going to do this right after we're done with the notes, and it's a really good review, and it's an ed puzzle. So a little change of how I would normally do this. Again, conduction you have to touch. So if I touch a hot pot handle, that's conduction, and I'm going to get burned. Within the pot, I have hot at the bottom, so I get convection currents swirling within here. And I have radiant heat from underneath the fire. Now, the fire could technically touch the bottom of the pot, but it doesn't have to, because the radiation from the fire will radiate upwards and a little bit out to the side, as you know if you've ever sat by a bonfire. Again, heat only moves from hot to cold. That's how it works. Even refrigerators, they are removing the heat from the items in your refrigerator, and that's why you have warm air that blows out of the back of a refrigerator or a freezer. Conductors. Conductors allow heat or energy to move from one place to another. So if you're a really good conductor, we can use that to transmit electrons, and we have electricity. Insulators then is a material that does not conduct electricity well or heat well, and we use insulators to grab that hot pot, and we also wrap wires around it to keep those hot wires from, causing fires in our house. That would be a bad thing. Insulators protect us, like the rubber tires on your car. Actually, it's also the steel cage makes all of the energy from a lightning strike go around you. But you can get treeing that happens, and if lightning actually strikes like the ground and there's a lot of silica sand, and if you are really careful and dig it out, you can actually see the shape of the lightning treeing that happened, because that silica sand will turn into glass. So here we go. Don't try this at home. Well, you won't have this at home, so I don't have to worry about that. This is a Faraday cage. Okay, I'm going to turn the sound off, because the point is this. He can touch that metal rod inside, because electricity is going to find the path of least resistance. So in this case, it wants to get to ground. That's why you shouldn't stand under a big tree, because if lightning hits the taller thing, it hits the tree, but the lightning will actually travel through the tree and through its roots. And if there's water there and it comes through, you can get electrocuted. In fact, that has happened, sadly, more often than you think, where a group of people under a tree have been electrocuted because of a lightning strike. This is what's happening. This is why your car also protects you, is your metal frame is the path of least resistance, and in this Faraday cage, or your car, the electricity is actually funneled around your car and down, and your rubber tires are also good insulators. They don't like to convey electricity. This is grounded into something else where it's actually going into ground. So this is something we're going to get to. We're not going to do a ton of this math, but you need to be aware that it happens, and you should probably write this on your formula sheet. Specific heat then is the measure of the relationship between heat and temperature change. So the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 Kelvin, so that's 1 degree. Remember Kelvin, and if you remember back from a long time ago in 8th grade, 1 Kelvin and 1 degree Celsius. Kelvin is just the Celsius scale shifted down by 273 degrees. So it's like raising 1 kilogram of a substance by 1 degree Celsius. But in this case, we say Kelvin because it's science, and science uses the freezing point of absolutely everything, like all electrons stop moving. So change in energy, there's a formula for that. Mass times specific heat times the change in temperature. So how much heat is required to raise the temperature of 5 kilograms of water by 10 degrees? Well, this is my mass, so I put that here, mass. Change in temperature is 10 degrees, that goes there. But then I would have to look up the specific heat of water, which in this case is 4,180 joules per kilogram times kilowatts. I'm not going to make you do this math, but I just want you to know that it exists, because when you get to chemistry, this is some cool math you'll get to do. By the way, if you multiply all this together, you get 209,000 joules of energy required to raise 5 kilograms of water by 10 degrees Kelvin. Congratulations, you made it to the end of the notes. The next thing you need to do is hit yes, I've gone through the notes. If you want to go and review any of those videos, they are available to you. And then you need to go on to the conduction, convection, radiation, Eureka video. Have a great day, and as always, if you need help, get a hold of me in class, on Zoom, whichever way we're working at the time. Have a good night.